So the last two things that we're going to mess with are a catalyst and then a specific type of gas. So basically, a catalyst does not shift an equilibrium. Now, catalysts do speed up reactions, so it will increase the rate of the forward and the reverse reaction because it speeds it up, but because it doesn't participate in the reaction, it won't actually like shift one way or another. So catalysts do not cause any sort of shift in equilibrium. You just have a quicker rate that is equilibrium is established. That's all. Okay? Now, adding an inert gas. So adding a gas to a system will increase the total pressure of the system because gases have pressure. Yes? Sorry? Okay. So the addition of the catalyst does not cause a shift in equilibrium. And then addition of an inert gas. Now, the word inert means unreactive. So like your noble gases are often referred to as inert gases because they're really stable and they don't react. So I think the confusion becomes is we know that if you mess with the pressure of a system, if there's gases present, it can cause a shift. But it's going to cause a shift for things that can react. So if you put a gas in there that doesn't react with anything, it just like floats around and minds its own business, even though that there's a total increase of pressure, it's not reacting with anything, so it can't cause a shift because like you'll increase the pressure and it'll bump into something and not do anything. So adding an inert gas also does not shift the equilibrium. So catalysts and unreactive or inert gases do not shift equilibrium. All right, so we're gonna do one last ice chart. So this is a chemist mixes 80% nitrogen and 20% oxygen by moles in a vacuum and finds that the total pressure is 1 atmosphere. Well, this is the old gases chapter, like partial pressure times mole fraction gives you total, or total pressure times mole fraction gives you partial pressure. But it doesn't have to be that complicated, right? If you know 80% of the pressure is coming from nitrogen and the total pressure is 1, then 0.8 of the pressure is coming from nitrogen. Mathematically, though, it looks like this. The partial pressure of any gas is the mole fraction times total pressure. And mole fraction is just a percentage. But it's a percent in decimal form because like 80% means 80 divided by 100. That's what that means. So you would do 0.8 for the partial pressure of nitrogen, 0.8 times total pressure, 1 atmosphere. And so the partial pressure of nitrogen is 0.8 atmospheres. And then you would do 0.2 for 20% times 1 atmosphere. So the partial pressure exerted by the oxygen is atmospheres. So these are the initial pressures. These are before they react, okay? Now, they give you K at this temperature, 25 Celsius, and they ask you to find the equilibrium partial pressures. Well, if you give an initial and they ask you for equilibrium, ice charts are helpful to organize our information. So on the next slide, I have an ice chart kind of drawn out for you. So this is 0.8 atmospheres. So what are the kinds of things we can plug into an ice chart? Well, in this chapter, we've plugged in concentrations and pressures, atmospheres, and we've actually been able to use moles too, right? When we've assumed, when the volume has stayed constant, like it's been the same for all of the species, okay? So we shouldn't have any product initially unless they tell you, right? This is at equilibrium, and then balanced, it would look like this. So now if we're at equilibrium, an equilibrium expression would be helpful. So let's write out the equilibrium expression. It's K equals products over reactants raised to their respective coefficients. Now instead of brackets, I'm going to write P for pressure of NO because we're actually using pressures right now and not concentrations. and then raised to the second power, divided by the partial pressure of nitrogen on the bottom, and the partial pressure of oxygen on the bottom. Okay. Now, K is actually given. It is super tiny. 1.0 times 10 to the negative 30th. Oh my gosh. Okay. What does a low small value for K mean? Very, very heavily what at equilibrium? Reactants, right? A small k means a big denominator, and your reactants are in your denominator. So that, I mean, that's like tiny. I think this is the smallest k we've seen so far. Okay. Now, when k is given, now this isn't always true, but when k is given, it's a hint that you might have to let x equal something because you don't have enough information to like plug in here. Now, when k is not given, it's because you're usually solving for it. So you have enough info to solve for it. Now that it's given, you're trying to solve for one of these guys. In fact, they're asking you what the partial pressure of every gas is at equilibrium. Well, I don't know equilibrium. Oops, I wrote 0.8 here. This should say 0.2, right? Sorry. You don't know equilibrium, you just know starting amounts. So that's what the ice chart will help us do. So we're gonna now I told you that the trick was to pick a product, and you pick a product that you only have one of. Now we're kind of stuck because there's only one product and you have two of them. So my strategy this time is to call this 2x. And the only reason I'm doing that is because I hate fractions. Okay, so let 2x equal the pressure of NO at equilibrium. Again, this is just so I don't have to work with fractions. If you called this x, then this would be 1/2 x and 1/2 x. Not a big deal. So equilibrium, this guy is 2x, which means I must have gained 2x. And remember, your change row, this row, is where you do your stoichiometry. This is your mole to mole ratios. If I produced 2x here, it's because I must have lost x amount here, right? A 1-to-2 ratio, and lost x amount here. So, and then the I row and the C row combine 0.8 minus x to get you E. And now that we have our equilibrium values, we plug into the equilibrium expression. So why is there a 2 in the 2x? Because there's a 2 as a coefficient. So I called this guy 2x, so I could call these guys x and x. If I called this guy x and not 2x, this would have to be 1/2 x and 1/2 x, and I don't want to deal with fractions. So I'm choosing not to. I'm just avoiding the fractions. All right, so now I'm going to plug in with even with my variables. So this guy is 2x. Sorry, it's kind of crammed. Now, I think I misspoke yesterday when I was doing this. I was going a little too fast. This part right here, so right now if we were to solve for x, we would be forced to do the quadratic, which is awful. Nobody wants to do that. I don't want to do that. You don't want to do that. And the nice part is, in this class, we don't have to do that anymore. So by doing what I'm about to do, where I assume x is much smaller than whoever I'm subtracting from. Well, technically I'm subtracting from two things now. So pick the smaller of the numbers. If x is smaller than 0.2, it's definitely smaller than 0.8, okay? So if x is much, much smaller than 0.2, then it's also much, much smaller than 0.8 because 0.8 is a bigger number. And that allows me to say, see you later. Because if x is really, really small, when you subtract it from that number, it doesn't change that number by all that much. Now, again, I want to kind of reiterate this misconception because a lot of kids go, well, if x is small, how come this top part just isn't 0? Like, why is this x not 0? I didn't say x was 0. I just said it was small. It was smaller than 0.2. I didn't call it 0 because if I did call it 0, you're right. There'd be no point of doing this. Everything would be the number 0. So you can't just like get rid of this top part. Nothing is being subtracted up here. So yes, it's small. Maybe it's close to 0, but it's not going to be 0. Okay? So that's why the top part doesn't just go away. So now I solve, right? So I multiply this side. Oh, I should have done this over here. I multiply k. I'll put it up here, but just, oops. By 0.8, right? And 0.2. All right, and that will get rid of it down here. And now be careful, 2x and squared, you've got to square the 2, and you also have to square the x. So this is really 4x squared up here. Let me do this. So then to get x, I have to divide by 4, and then square root. I'll let you try to work that out. I'll write what I get. So I got x to be 2 times 10 to the negative 17th. Well, that's like really small, right? So we definitely know our assumption is true. 2 times 10 to the negative 16th is definitely much smaller than 0.2. So if I were to ask you the pressure of NO, it would be, this is atmospheres, right? This is 2 times this number. So the pressure of NO is 4 times 10 to the negative 16th atmospheres at equilibrium. So basically nothing. Now, you can go ahead and try in your calculator, but if you take 0.8 minus x, which is 0.8 minus 2 times 10 to the negative 16th, it's so small, your calculator literally will spit 0.8 back out. And if you take 0.2 minus a number, it's going to spit 0.2 back out because that number is so small. So basically, as we had recognized with such a small k, at equilibrium, it's basically all reactants and very little product. 0.8, 0.2 pressure, atmospheres, and then 4 times 10 to the negative 16th atmospheres for my product. Very little product at equilibrium. Okay, so that was only the first part of this. The next part is where we're going to talk about Q and Le Chatelier and shifting. So what they say in the next, so I got my equilibrium pressures. They're 0.8, 0.2, and 4 times 10 to the negative 16th. But the next part asks you, it says if the temperature increases, so the temperature was 25, and now it's increased into 2,127. Okay? And they tell you what happens to K. So this was the K value for this temperature, and this is the new K value for this temperature. So we have to kind of go through this like domino thought process. What I mean by that is, let's take it step by step. K is increasing, right? 1 times 10 to the negative 30th to 0.02025 is definitely an increase in K. Well, K equals products over reactants, right? So if K is getting bigger, who is getting bigger? Products or reactants? What causes K to increase? An increase in who? products, right? A bigger numerator will let K shoot up, right? Get bigger. So products must be increasing in in pressures. I guess this one's about pressures. So whether a reaction is endo or exothermic, we have to decide which side the heat is going to be on. So if you can't just like look at this, the best way to do is to put the heat on both sides and do what the problem is saying it's doing and figure out which way it's shifting and which way it needs to match. So reactants going to equilibrium with products, right? I'm going to start off with heat as a reactant, okay? Meaning endothermic. So if I have it like this, I am increasing heat, right? 25 to 2127 is an increase in temperature. So if it's endothermic, I am adding stress to the side with heat on it, which in this case is a reactant. So if I increase temperature, I increase heat, which way will I shift? To the right to alleviate that heat. Shifting to the right will cause this to go up, right? Does that match what we just said needed to have happen? Did my products go up? So K gets bigger, so it is endothermic. Let's talk about why it's not exothermic, okay? If it was exothermic, my heat would be written as a product. That's what it means to be exothermic. Heat comes out, it exits the system. So heat is written on the product side. So if I'm increasing temperature, which I am, I'm going from 25 to 2127, I would increase the stress that the heat is on, which in this case is the product side. So now if you have too much heat over here, you're going to shift to the left, which means reactants will get bigger. Well, if reactants get bigger, K gets smaller. So that's not good because K is definitely getting bigger from here to here. So that's why it's not exothermic. Questions? All right. So this slide right here, I'm not going to go over. What this is if you're struggling with understanding like the concept of Le Chatelier and providing stresses to a system at equilibrium and which way it shifts, this will summarize two different processes, okay? Everything we've just done on a slide in summary. The RHS and LHS is right-hand side, left-hand side. That's what they're trying to tell you which way it's moving. So RHS is right-hand side, LHS is left-hand side. So this is one type of summary. You can look at all the different ways you could stress out this system and which way it would shift and why. And then another type, which way you could have different ways you can stress the system and which way it would shift and why. All right. So these two slides are a really, really good summary for additional kind of like reinforcement of Le Chatelier's principle. So I'm going to start you off on this one, but I'm going to let you work on it on your own. I didn't get as much participation last period, but my third period was like they were all spitting out their answers in the chat and trying to, you know, when someone got it wrong, they were trying to explain to each other why it was this or why they thought it was this, which is really like the best way to work out problems is if you aren't sure how to do it, the best way to reinforce learning is to be able to teach someone else to kind of show that you understand. So there's no reason to if you get these wrong that it's a big deal as long as we just figure out, you know, why it's the right answer. So first things first, D stands for delta. My triangle didn't transfer over. Delta H. So when they say delta H is less than 0, they're telling you delta H is negative. Well, delta H being negative means this process is exothermic. That's what they're trying to tell you. So when I see this, the first thing I would do is I would put heat on the correct side of the equilibrium arrow. And if it's exothermic, the heat will be on the product side of the equilibrium arrow. Now, I'm going to give you a minute or so, 2 minutes maybe, to try to answer the question, please. So let's talk about these stresses and what they're doing. So we're making ammonia in the presence of a catalyst, so it helps make it faster, okay? Which of the following would cause more ammonia to be present? So let's work through the thought process of what that means. Well, if more ammonia is present, it means I'm increasing the amount of ammonia. In order to increase the amount of ammonia, I need to be shifting towards ammonia, okay? So I need to apply a stress that will allow me to shift towards ammonia so I can make more ammonia. So the first option was increase the temperature. Well, because this is exothermic, if you increase the temperature in this situation, you add a stress to the product side because that's where the heat is, which means I will shift to the reactants. That is not going to help me make more ammonia. Okay, so that's out. The next option is decrease the volume. So you go, okay, well, what does that do? Decreasing the volume increases the pressure. Okay, now this will have an effect only on our gas particles. All right, and in this this reaction, they're all gases. So increasing the pressure, it will increase the pressure of the overall system. Okay, now when you increase the pressure, how many gas particles you have plays the role on which side is the most stressed. So as reactants, I have 1 nitrogen and 3 hydrogens. So there's 4 gas particles over here running around. Okay, my product side has 2 running around. So remember, the more gas particles you have, the more pressure you have. More gas means more pressure, meaning increasing the pressure will have the biggest stress on the side with more moles of gas, meaning my reactant side will be the most stressed under this set of circumstances. And if this side is too stressed, I'm going to shift to the right and make more ammonia. In fact, if you remember back when I introduced the Haber process, I said that this reaction is done with a catalyst under high pressure because high pressure forces you to make more ammonia. Okay? Now, I want to talk about why C and D don't work. So C says add a chemical that reacts with hydrogen gas. Well, if you add a chemical that reacts with hydrogen gas, in essence, you're going to lower the amount of hydrogen gas in there. So what's the equilibrium going to want to do? Well, it's going to want to shift back that way to get it back, to make it up, because you're taking it out. Okay? So that's why this is out. So obviously, removing nitrogen would have the same effect. You take some of this guy out, it's like, don't do that to me, and it will try to shift back that way to make up some of it, get some of it back. So that's why D is out. Questions? All right, let's try another one. Now, I realize that the question is the same, but the answer options are not the same. So again, I have the same exact reaction, the Haber process. The delta H is less than 0, meaning it's negative, meaning it's exothermic. So I'm going to rewrite my heat as a product again because it's exothermic. And now it's the same exact process. They want you to make more ammonia, but they have different stresses in this problem, or a few different stresses. So I need to increase ammonia because that's what it says, which means I need to be shifting towards ammonia. How can I stress the system to cause more ammonia to be produced? So I'll give you a minute or so on that one. Okay, I have to re-record this because I forgot to hit the record button. So again, decreasing the temperature means I'm going to lower the heat, and the heat is a product, which will cause the reaction to shift towards the products to try to get it back, make up for it. Increasing the volume drops the pressure, and to get pressure back, it will shift to the side with more moles because that will get you pressure quicker, in essence. Adding a chemical that will react with hydrogen gas would remove hydrogen gas, so it would shift back this direction to get it back, to reestablish equilibrium. And then the catalyst with more surface area would just cause the reaction to get to equilibrium faster. Okay? Not necessarily not make more product, just get there faster. All right, this last one was the one I just had a Murphy moment yesterday. I made it way more complicated than it needed to be. So they give you a reaction, and they say, okay, they're added to a 10-liter container, so they're all in the same container. They're added at the same temperature. They all have a partial pressure of 0.1, and they react until equilibrium is attained. And they say, okay, which species will have the highest pressure at equilibrium? Well, there's no math necessary for this. Look at the value of K. Is K big or small? That's 2,000, right? Which is pretty big, yeah? So if K is big, you have mostly what at equilibrium? Products. So who's going to have the highest pressure? C, NOCl, your product, because K is so big. Yes, if that last problem was endothermic, that would not have worked. There would have been no right answer. If the last problem was endothermic, there would be no right answer. Because removing heat from an endothermic process would cause the reaction to shift to the reactant side, so you couldn't make more ammonia. Okay, I'm finished with this, the slides. Now we're going to do the demos. I'm going to give you a second, please, to write down this reaction on the board. I have two reactions, actually. Flashback to chapter 4, where we made solutions, and I want to do this with you. Sorry if you find it annoying, but because you have not had any experience in making solutions, which is like a huge part of chemistry, is being able to make a solution. So I'm going to make one for you ish. I'm going to kind of go over the basics. So when I had to make these, like I had to make this guy in the lab, and then this is going to be, well, I'll tell you later. I had to make the cobalt 2 chloride solution, and I had to make this, we also have a silver nitrate solution that I'm using. And so you go, well, I didn't just like pull it out of the cabinet, unfortunately, I had to make it. So you go, well, how did you make it? So I need you to write this down, and you have to have like a big flashback to how you prepare solutions. So the solution that I needed for this demo was 0.1 molar. So write that down, 0.1 molar. That's the concentration that I needed it to be. And I decided to make 250 milliliters of it. So you need to write that down also. So basically, I made 250 milliliters, 0.1 molar of my cobalt 2 chloride hexahydrate. Now, in order to do this, you need to know the molar mass of cobalt 2 chloride hexahydrate. I'm not going to make you calculate it. I'm just going to tell it to you. It's 237.9 grams per mole. So, we seemed a little rusty in all the classes. I'm assuming that's going to be true for this. How do I do it? Well, I went in the back and I got cobalt 2 chloride hexahydrate. Here it is. It's in this container. Obviously, it's a solid. Okay? What do? I literally hand you this bottle and I say, go make it. Right? So, like, no one has any idea what they're doing right now, right? So let's remember, if I hand you a solid, I'm probably going to have a certain mass of it to use in the solution, right? So if I know the molarity that I need it to be 0.1 molar. That's what the demo instructions say. And I need 250 milliliters of it. Remember that molarity times volume is moles. Be careful though, right? Molarity is moles per liter. So your volume needs to be in liters. It cannot be in milliliters for this. This is not a dilution. I'm not diluting anything. Now, if I was diluting, I could leave it in milliliters, but I'm not. So basically, you should take 0.1 and multiply by 0.25. That will give you moles. Remember, molarity times volume is moles. This is a good little review of chapter 4. Now I hand you this and I say, okay, go measure some moles. Like, what? Like, do you think I have a tool in my classroom? And you might, but that measures in moles. Because I don't. I don't have any kind of thing in my class that measures in moles. I do have something that measures in what? Grams, right? My trusty electronic balance can measure in grams. So if I know moles, can I turn it into grams? I do that using molar mass, right? And I told you its molar mass was 237.9. So how many grams of this stuff, this guy, am I massing out? You guys tell me. Molarity times volume gets moles. And you can use molar mass to go from moles to grams. Thank you, Micah. Yes. I got one right answer. 5.9-ish, right? Is what I'm getting. Are there any questions on that? So literally what I would do is I would take my cobalt 2 chloride, I'd go to my balance, I'd put a paper down or like a weigh boat down and I'd zero it. And then I would add 5.9 grams to it. Now, I have this beautiful 250 milliliter volumetric flask. This is often the container used for making solutions. You can also use graduated cylinders because they have really good markings on them. So the only limitation of this tool is it only measures one volume. Literally, if it's a 250 milliliter flask, it only measures 250. So like I can't make 100 in here. I mean, I can, but I have no idea where 100 is. So the reason graduated cylinders can sometimes be better is because they have lots of markings on them. But again, you will never ever make a solution in a beaker, ever. Okay, the beakers have like 3 marks on it and that's it. They're horrible. You can make your solution and then dump it into a beaker, but you're only going to either use a volumetric flask or usually a graduated cylinder. Now this flask has 1 mark on it. It's right here. And that mark means exactly 250 milliliters. It's perfect for 250 and horrible for anything that's not 250. Okay, but I said I wanted to make 250, so this is great. So what do? Well, I have my 5.9 grams. Okay, let's pretend this is 5.9 grams. Okay, I dumped some of it in here. Now you can already have a little bit of water in here if you want. If this was an acid, which it's not, but if it was, you would have to have water in here first because acids with water release heat and you want there to be some insulation in here so the glass doesn't break and you drop acid all over yourself. Okay, so look, I have my solid in here. Add some distilled water, right? I'm making a solution, an aqueous solution. Now, do I fill straight up to the 250 right away? Do you remember what is supposed to happen first? You need to get all of the solid to dissolve before you fill up to the final mark. So the reason that these are cool is because see how well I can like swirl this? Okay, and I didn't get it all to dissolve, so I'm gonna add some more water, right? You can still add more water. You just don't wanna fill up to the mark right away, okay? You wanna get it all to dissolve, blah, 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 okay? And then you would fill up to this mark and you would have 250 milliliters of 0.1 molar cobalt chloride hexahydrate solution. Okay? And look, it's this beautiful, this cobalt 2 chloride hexahydrate is like this beautiful, like pinkish, reddish color. Okay? So that's how I made this. This is I just put it in a container. Okay? That's how I made it. Questions? Okay, so we're gonna not start with that one. I also did that for the silver nitrate. So like I did the same amount. I did 0.1 molar, 250 milliliters. Now it was a different mass because silver nitrate has a different molar mass than the cobalt. But my silver nitrate is also solid, so I made the solution from a solid and then mixed with water. Yeah, the moles should be 0.025, right? 0.1 molar times 0.250 liters is 0.025 moles. Very good. So again, I also have silver nitrate for that demo that I'll be showing you. But for right now, I'm going to do a different one. I need to give me a second. I got to go get some ice. So the first reaction we're going to do is this bottom one here, the dinitrogen tetraoxide in equilibrium with nitrogen dioxide. And I have these tubes kind of like I showed you on the in the slides, if you remember seeing them. So these are equilibrium tubes that have both of these gases in them. Obviously, well not obviously, but the dinitrogen tetraoxide is colorless. So again, we don't use the word clear or white, okay, in here. If something doesn't have color, like we call it colorless. And nitrogen dioxide gas is brown. And it's actually a toxic gas. You would never want to inhale it. Now, like, let's say I smashed this on the ground right now. There's not enough of it that it would like cause a big problem, but in big amounts, this is a toxic gas, okay? Now, obviously, if a gas is colorless and another gas is brown, it's going to look brown. Like, there's no way around it. But I'm going to be able to make them more and less brown by messing with heat. Now, I can't mess with anything else. I can't mess with pressure in here. I can't mess with concentration because these are sealed. So the only thing with these I'm going to be able to mess with is temperature, okay? So it's going to be your job for you to figure out, based on me putting them in a hot water bath, that would be increasing heat. And a cold water bath, that would be me decreasing heat, whether the process as written is endo or exothermic. So I'm going to move my, okay, you can hopefully see this is a hot water bath right here, and this right here is a ice water bath, okay? And I'm going to put this guy in here. And I'm going to let it set for a second. This isn't like an instantaneous thing. Okay, this is water is boiling. I don't know if you can already tell. I don't know if you guys can tell. Is it getting darker or lighter?
Lighter.
It's definitely getting darker. Now, I'll give it a minute. It's going to take a second, okay? That I'll pull them out and you'll be able to totally tell the difference. I'm going to leave this one just at room temperature, okay? The longer it sits in there, the darker it's going to get, okay? So, in other words, heating it is causing the equilibrium to shift this way. How do I know? Well, it's turning more and more brown, meaning this guy is increasing in concentration. So adding heat is shifting my equilibrium to the product side. So which side is the heat on? Is heat a reactant or is heat a product? So when you're unsure, try it on both sides. Try it on one side and then try it on the other. So let's look. If I put heat here as a reactant, I would say this is endothermic, right? So adding heat would add the stress over here, causing me to shift that way. So it is a reactant, right? If it was a product, heating it would turn the tube less and less brown. So I'm going to kind of hold them up so you can compare. This is the one from the hot water bath, and this is the one that's at room temperature. Hopefully you can see the difference in color. This one's definitely darker than the one that's at room temperature. This one was in the hot water bath, okay? So I'm going to put this one in here, my dark one, my really, really dark one, okay? And then I'm going to now stick it in the ice water bath. And I'm going to take the one at room temperature, and I'm going to put it in the hot water bath. And I'm going to let it set for a second. Okay, now if you're in here, I don't know if you guys can see, you can like literally see the brown smoke kind of shooting up into the tube, the equilibrium tube. And now this one's a little bit funkier because part of this is submerged in the ice and this is room temperature. So this one's going to actually kind of look like two different colors. I'll take it out in a second. Maybe I'll flip it. Oops. Yeah, this one's kind of old and funky, I think. Let me grab another one. Hold on one second. I don't know. Okay, that one's better. You can see it better. It's like condensing on the side or something.
Yeah, I was gonna say it looks like there's like bubbles.
Yeah. So very, very easily, you should be able to see quite the color difference. This one is really dark compared to this one that is really light. So when you put this in the cold water beaker, you are removing heat. That's what it means to lower the temperature. So removing heat means you're taking this away. Well, making this go down causes the equilibrium to shift back this way, so the tube becomes more and more colorless, which is why it's lighter. Now, unfortunately, I don't have temperature to get it colorless. I don't have anything that cold, but if I had lower temperatures than just ice water, I could get it to go to colorless or pretty close to colorless because I would have an abundant amount of this at that moment. So now if I take them out, it should be very, very obvious that this is lighter than this one, okay? And then I can just keep switching them, right? I'm going to do it. Hot water now. Cold water now. Okay? And then you can just do this over and over again forever. I mean, these tubes have been in here since before I started teaching here. Who knows how old they are, okay? assuming that they don't break, right? And then it escapes and then it's over. But again, this equilibrium is forever in essence, all right, because they're trapped and sealed off in a closed system. So I think I had some questions. Let me look. The glass is pretty durable. The rapid heating and cooling, I guess, could, but this is like pretty good glass. Like a less lab type glass absolutely would probably crack if I kept doing that. But this is definitely more lab quality glass. Okay, so if you notice, and you know what's really cool, this is how I like, if you look like at the top of this one, like it's still a little dark, and then I'll pull, this part is colder down here, right? Look, it's lighter at the bottom. So it's a little darker on the top and then lighter at the bottom. So I'll just kind of stick here. All right, but again, I have now switched it. I heated this one up, cooled this one down, super dark brown, super light. Okay, are there any questions on this equilibrium demo? Pretty cool, but the next one I do is it's not cooler, I just like the colors better. Okay, all right, I'm gonna take these out then. And we're gonna hope this is not a crappy one like it was second period. Okay, so I've got my cobalt 2 chloride hexahydrate, and I got a test tube right here. And I'm just gonna put a little bit in here. Okay, got a little bit in here. It's pink, very, very pink. All right, and so I'm basically in terms of my reaction, I'm right here. All right. I am going to add, I better get my goggles ready, 12 molar hydrochloric acid. I don't know if you know, but 12 molar is like super nasty. Like burn through your pants, burn through your clothes, gonna burn your skin if it gets on you. Okay? My hydrochloric acid is right here. It looks just like water, but it's not. Do not drink. Okay? And I want you to tell me, hydrochloric acid is HCl, right? I want you to tell me, given my reaction, if I add HCl, which way is my equilibrium going to shift? And now this is where kids get kind of stumped because you don't see HCl written up there. But it's there, sort of, in a way. Who is it? Yeah? Where's the H? Who cares? Spectator ion. Okay? So in essence, if I'm adding HCl, I am increasing the concentration of chloride ions by adding Cl, right? Well, if I increase the chloride ions, which way shall I shift? Right, or to the product, right? Well, when I'm shifting this way, it means this should be going up and these should be going down. So visually, what's neat about this equilibrium, and like the other one, is there's colors that allow us to see the equilibrium. Whereas if you have like everything colorless, like visually, it's not the equilibrium's not happening, it's just like we can't see it. So what's cool about this one is there's colors involved so we can watch the equilibrium shift. So this should turn what color? Blue. If we're shifting this way, we're making more and more of this, so this should get more and more blue. Okay? So let's try. So I got my HCl down here. Got my little test tube. Okay. Purplish. Yep, that's pretty blue. Yeah? Blue? Okay. So now I'm heavily over here. I obviously have way more of this guy than I do right now, than the other cobalt right now. Okay, great. I'm gonna take this guy. This is where it went south, second period. I'm going to put it in a cold water bath. Okay? That means I'm removing heat. I could also put it in a hot water bath and see what happens, right? Add heat or remove heat to try to figure out which side of the equilibrium arrow the heat is on. So here's my ice water bath right here. Let's see. Fingers crossed. So I just have it sitting in there, right? Okay, now this isn't going to be instantaneous. I'm going to get my stirring rod so I can kind of keep it mixing. It's not even a stirring rod, it's a thermometer. But whatever. Let's see if I can get this to work. It's changing a little, but let's keep going. I'm going to pause my recording so people don't stare at me for... Let me start over. I forgot to record. So removing heat is turning it pink, whereas adding heat, it's not quite blue yet, but it's purple. It's going from pink to purple and eventually will be blue, right? Okay. So adding the heat up here is shifting it to the blue. Okay. Now you could really like take the and move these back and forth like we did the nitrogen dioxide equilibrium tubes. But instead, I want to do something else. I'm going to get this guy back to blue just real quick. I'm just adding more HCl to get it back to blue, okay? So I'm shifting the equilibrium by doing that. I just want it to be blue, not purple. Still purple. Is it blue? It's blue. Okay. All right, so I'm back to blue. I added enough HCl to get it back to blue. Now, I'm going to add silver nitrate to this container, or this test tube. Does anybody know who it will react with in the reaction? So look at who we have. Now, it's not going to be the nitrate, right? Nitrate ions are always soluble. So it's not going to be the nitrate, it's the silver. The silver actually will react with one of the species in here. Do you know who it is? Cl. Very good. Silver, when it sees chlorine, reacts, it precipitates out a solution. Silver chloride is a precipitate. So if there's silver ions floating around and it sees a chloride ion, it yanks the chloride ion out of solution and turns into a white precipitate. So by adding the silver nitrate, this guy's going to react. Well, what does that mean, react? That means it will drop in concentration, right? If it's reacting, there's less of it in there. Well, if this guy drops in concentration, which way is my equilibrium going to shift? Back this way, right, to try to get it back, which means this should turn what color? Pink. So my silver nitrate is right here. And here's my blue test tube. It's looking a little purplish now. I'll get it blue, guys, don't worry. It's being stubborn. There we go. That's blue. Blue, blue. Okay. Here's my silver nitrate right here, solution that I made. Okay. I want to put it in here. Ready? Now, it's going to precipitate, so I should see a solid form, yeah? But it should also turn pink because the removal of the chloride ions, because they're part of a solid now instead of floating in a solution, should shift my equilibrium. Oop. Okay. Now, I'm going to stir. It definitely went back to pink, yes? And now I'll let it settle. Once I let it settle, you'll be able to see the white precipitate sitting at the bottom, okay? And the solution went back to pink. right? Okay, so I just shifted it again. Now, I want to get it blue again. So hold on one second. I have a couple ways. I could add chloride, but instead, I'm going to just dump some of this out. I'm going to take this guy, and I'm just going to put it back in the heat to see if I can get the blue back. Now, because class is over, it's probably not going to get all the way back to blue, but you can kind of sit here and hang out and see that it will start changing at least to purple before you guys have to head out. It's already going. I don't know if you guys can see from there, but you guys can probably see it's already starting to turn. And again, it would just go back to blue by applying the heat, okay? And again, you can just mess with this stuff over and over and over again until the chemicals aren't present anymore. Oh, it's almost blue. Wow, this one went faster. Friday! So if you guys can see that, yeah, that's definitely turning blue in there now, right? Maybe more of a purple, but back to blue. Okay? And then I could just put it in the cold water bath. Turn back to pink for me, please. And just do this over and over and over and over and over and over again. Look, you can already see it's turning back to pink. Okay? All right, I hope you guys have a good weekend. I hope this helped demonstrate